Welcome back, everyone. Ready for another deep dive?
Always.
Awesome. Today we're tackling an article literally titled, "The Universe is Stranger Than We Thought." And let me tell you, just from reading it, it lives up to the name.
I was just thinking that myself. I mean, it's incredible how much astronomy and astrophysics has changed even in the last few years.
Seriously. It's like every time we think we've got a grasp on things, the universe throws us a curveball.
Exactly. And these curveballs, as you put it, are seriously making us rethink basic assumptions about how things work out there.
So, like, what kind of assumptions are we talking about here?
Well, take planets, for example. We used to think, all planets are basically like the ones of our solar system. Rocky planets close in, gas giants farther out. Pretty straightforward, right?
Yeah, makes sense. Our solar system's our only model, right?
Right. But now we're finding exoplanets, planets around other stars that totally break the mold.
Yeah, exoplanets. I remember when the first one was discovered back in '92. It was huge news.
Huge. And since then, we've found thousands more. The diversity is just unbelievable.
I remember reading about those, what are they called, super-Earths and mini-Neptunes.
Those are some of them, yeah. They're bigger than Earth, but smaller than Neptune. And some of them might have these huge oceans.
Oh, things on other planets. That's just crazy.
Right. And then you've got planets with, truly extreme conditions.
Extreme half.
Like, take WSP 76b. It's this gas giant so close to its star, it's over 4,000 degrees Fahrenheit.
Whoa. Anything can survive that.
Nope. And get this. It rains molten iron on WSP 76b.
Wait, molten iron rain. How is that even possible?
Well, it's tidally locked, meaning one side always faces the star.
Like our moon always showing the same face to Earth?
Yep, exactly. So the day side is blasted with constant heat, while the night side is relatively cooler. And that temperature difference creates these insane winds that carry vaporized iron from the hot side to the cooler side.
So like iron evaporates on one side and then rains down as molten metal on the other.
Pretty much. It's wild.
That's nuts. So if planets can be that different from what we imagined, what else is out there? I mean, what other crazy stuff might we find?
That's what's so exciting. We're just getting started with exoplanet discovery, and every new planet we find changes our understanding of, planetary formation and the possibility of life beyond Earth.
So you're saying there might be even weirder planets out there than WSP 76b?
Oh, absolutely. We've only scratched the surface.
Okay, so we've got super hot planets, but what about, like, the opposites? Are there planets that are super cold, so far from their star that they're just alone out there?
As a matter of fact, there are. We call those rogue planets. They don't orbit a star, just drift through space all by themselves.
Rogue planets. That's kind of a lonely existence for a planet. How do they get out there like that?
That's the million-dollar question. Astronomers are still debating that. Some think they were, kicked out of their original solar systems, maybe a gravitational interaction with another planet.
Like a cosmic game of billiards.
Yeah, exactly. Others think they formed independently from collapsing gas clouds, just like stars do, but on a smaller scale.
So they might have never had a star to begin with.
It's possible.
Wow, that's fascinating. But could a rogue planet ever, be habitable? I mean, we always talk about the habitable zone around stars, but what if? What if there's life that doesn't need a star?
Now, that's a thought-provoking question. It really challenges our assumptions about what habitable even means.
Right. We just assume life needs a star like our sun.
Exactly, but maybe that's just, our Earth-centric bias. Life on a rogue planet might use internal heat, like from geothermal activity, or tidal forces from a moon, if it has one.
So even in the dark depths of space, life could find a way.
It's possible, and that's what makes exoplanet research so exciting. The universe is full of surprises.
It definitely makes you realize how unique our own solar system is.
Speaking of unique, there are some systems pretty close to us that are especially interesting for the search for life. Have you heard of Proxima Centauri b?
Vaguely. Remind me.
It's a planet orbiting a Proxima Centauri, which is the closest star to our sun. And get this, it's right in the habitable zone.
Seriously. So it could have liquid water.
That's what we're hoping to find out. It's still tough to study atmospheres of planets that far away, but somebody suggests it might have a substantial atmosphere, maybe even oceans.
Wow. An ocean world on the planet orbiting the closest star to us.
It's a possibility. And then there's the TRAPPIST-1 system. It has 7 Earth-sized planets, 3 of them in the habitable zone.
7 Earth-sized planets in one system. What are the odds?
Right. It's a prime target for future observation, especially with the James Webb Telescope. We're really hoping to learn more about their atmospheres and whether they show any sign of life.
Wow, that's incredible. Okay, so we've got planets that are hot, planets that are cold, planets that might have oceans, but I think we need to move on to something even more mind-boggling. Black holes.
Now we're talking. Black holes are the ultimate cosmic mystery, right?
For sure. The craziest thing is we used to think they were just theoretical, a mathematical quirk of Einstein's theory of relativity. But now we have actual pictures of them.
Yeah, that image of the black hole at the center of Galaxy M87 a few years back, that was a huge deal.
Huge. And then they imaged Sagittarius A, the black hole at the center of our own galaxy.
It was a game changer. The Event Horizon Telescope, or EHT, used telescopes all over the world to basically create a virtual telescope the size of Earth. That's how they could image the shatter of the black hole's event horizon.
It was like looking into the abyss. But black holes aren't just cool to look at, right? They also, like, warp space and time. What's the deal with gravitational waves?
Ah, gravitational waves. These are ripples in space-time caused by, you guessed it, massive objects like black holes.
So it's not just space that's warped around a black hole, it's time too.
You got it. Imagine space-time like a giant trampoline, and a black hole is a bowling ball sitting on it.
Okay, I can picture that. So the bowling ball makes a dip in the trampoline. That's like how a black hole warps space-time.
Exactly, and anything that gets too close to that dip falls in, including light. That's why they're black.
Makes sense. But where do the gravitational waves come in?
Well, when massive objects like black holes collide or even just orbit each other really closely, they make these ripples in space-time.
So like the trampoline itself is vibrating from the impact.
Yeah, exactly. And we can actually detect these vibrations with these super sensitive detectors called LIGO and Virgo.
So what have we learned from listening to these space-time ripples?
Well, for one, we've learned that black hole mergers are way more common than we thought. It's like these cosmic crashes are happening all the time.
Wow, that's kind of terrifying, but also really cool. What's been the biggest surprise from gravitational waves so far?
That's tough. But one of the biggest has been finding black holes that are way more massive than we thought possible. Like one event involved a black hole 100 times the mass of our sun merging with another black hole.
100 times the mass of our sun. How does something that big even exist?
That's one of the biggest mysteries in astrophysics. We're still trying to figure out how those supermassive black holes form. It's possible they're the result of smaller black holes merging over, billions of years.
So like black holes keep eating other black holes and getting bigger and bigger.
Like a cosmic snowball effect. And then there's this monster of a black hole called TON 618. It's estimated to be 66 billion times the mass of the sun.
66 billion. That just bogles the mind. How can something that massive even be a thing?
It's a real puzzle. Our current models of black hole formation can't quite explain how something that massive could have formed since the Big Bang.
So any theories about how TON 618 got so big?
Well, there are some ideas out there, but nothing conclusive yet. One idea is that it formed super early in the universe, maybe even before galaxies formed.
Before galaxies. Wow.
Another idea is something called direct collapse. That's where a huge cloud of gas collapses straight into a black hole, no star formation involved.
So like a black hole shortcut.
Yeah, sort of.
Fascinating. Okay, so black holes are out there, merging, growing. But what about closer to home? Any black holes living in our own solar system?
You never know. Remember Planet 9, the hypothetical one that might be out there beyond Pluto?
Yeah, the one they haven't actually found yet.
Right. Well, some scientists think Planet 9 might actually be a primordial black hole.
Wait, a black hole in our solar system? Seriously?
It's a possibility. Primordial black holes supposedly formed right after the Big Bang, and some could still be around.
So there's a chance, however small, that there's a black hole hanging out in our cosmic backyard.
It's an intriguing possibility. Some astronomers are actually looking for evidence of a primordial black hole in our solar system.
Wow, that would be a huge discovery. Okay, I think we need to move on from black holes for now. My brain is melting.
I hear you. What do you say we dive into the world of neutron stars?
Neutron stars, aren't those like the super dense leftovers of dead stars? I remember reading that a teaspoonful of neutron star material would weigh billions of tons.
You got it. They're like giant atomic nuclei packed so tight that a sugar cube-sized piece would weigh as much as Mount Everest.
Okay, that's just insane. What makes them so dense?
Well, when a massive star dies, it explodes as a supernova, right? And the core of that star collapses under its own gravity.
Right, so it implodes.
Exactly, and all those protons and electrons in the core get squished together and form neutrons.
So it's just a ball of neutrons, hence the name.
Exactly, a super dense ball of neutrons.
Okay, that makes sense. But what happens to all the stuff that doesn't get squeezed into the neutron star?
That stuff gets blasted out into space during the supernova explosion. It creates those beautiful nebulae we can see with telescopes.
Right, the colorful clouds of gas and dust. Amazing. Okay, but back to neutron stars. They come in different types, right? Like, what's the difference between a pulsar and a magnetar?
Ah, good question. All pulsars are neutron stars, but not all neutron stars are pulsars.
Okay, I'm following so far.
So a pulsar is a neutron star that spins really fast, and it emits beams of radiation from its magnetic poles. As it spins, those beams sweep across space like a lighthouse beacon.
So if we're in the path of the beam, we see it as a pulse.
You got it. That's why they're called pulsars for pulsating star.
Ah, okay, I see. What about magnetars?
Magnetars are like pulsars with super strength magnetic fields trillions of times stronger than Earth's.
Trillions. Is that even possible? What happens with a magnetic field that strong?
Some crazy stuff. They can cause starquakes like earthquakes, but on a star.
Starquakes. Yikes.
Yeah, and those starquakes release tons of energy like gamma rays and X-rays.
Gamma rays. Aren't those dangerous?
They can be, but luckily most magnetars are far away, so we're safe.
Okay, good. But to put that magnetic field strength in perspective, it's like, what?
Imagine a refrigerator magnet so strong it could rip the keys out of your pocket from across the room.
Wow. Okay, magnetars are intense. But didn't I read something about magnetars being connected to those fast radio bursts?
You did. FRBs are these super bright, short bursts of radio waves that come from other galaxies. We still don't know what causes all of them, but some have been linked to magnetars.
So these things are super dense, super magnetic, and they blast out powerful radio signals.
They're overachievers.
That's crazy. Okay, so we've got spinning pulsars, magnetars. It seems like neutron stars are the opposite of boring.
You could say that, and we're learning new things about them all the time. Like we've detected these strange signals called glitches.
Glitches? Like what kind of glitches?
It's when a pulsar suddenly speeds up its rotation, like it gets a burst of energy, but we're not sure where it comes from.
That's weird. You'd think something as dense as a neutron star would be pretty stable, wouldn't you?
You'd think so, but the universe loves to keep us guessing. One theory is that it might be caused by something called a superfluid inside the neutron star.
Superfluid, what's that?
It's this weird state of matter that can flow without any friction.
So there might be a kind of frictionless liquid swirling around inside these incredibly dense objects.
It's a possibility.
That's mind-blowing. Okay, so this has been incredible, but I have a random question. Could there ever be life near a neutron star? I mean, it seems pretty intense out there.
That's a great question. It's definitely a harsh environment, but some scientists think life might be possible under certain conditions.
Really? Like, what kind of conditions are we talking about?
Well, imagine a planet orbiting a neutron star, but at a safe distance. If that planet had a thick enough atmosphere to block the radiation and a strong magnetic field to deflect charged particles, it's possible liquid water could exist on the surface.
So, life in the shadow of a neutron star. What would the sun even look like from a planet like that?
It wouldn't be like our sun at all. It would be this tiny, super bright point of light. And since pulsars spin so fast, that point of light would appear to pulse like a cosmic lighthouse.
Wow, that would be a sight to see. It makes you wonder what other weird life might be out there adapted to conditions we can't even imagine.
Exactly. Our definition of habitable is probably too narrow. Life is adaptable.
So true. Okay, so we've talked planets, black holes, neutron stars. But we can't forget the stuff that makes up most of the universe: dark matter and dark energy.
Ah, yes, the big mysteries. It's kind of humbling, isn't it? We've been studying the universe for centuries, but it turns out most of it is made up of stuff we can't even see.
Yeah, it's like we barely know anything. So what do we know about dark matter and dark energy? I mean, how do we even know they exist if we can't see them?
We know they exist because of their gravity. Like dark matter provides the extra gravity needed to hold galaxies together. Without it, they'd fly apart.
So it's like the cosmic glue holding everything together.
Exactly. And dark energy is even weirder. It's causing the expansion of the universe to speed up.
Wait, so the universe isn't just expanding, it's expanding faster and faster.
That's what the evidence shows. And we have no idea what dark energy is or how it works.
It's like the universe is messing with us saying, haha, you think you understand me? Nope. Seriously, though, any theories about what these things could be?
Lots of theories, but no definitive answers yet. Some of the top contenders for dark matter are hypothetical particles called WIMPs and axions. For dark energy, it could be a property of space-time itself, like Einstein's cosmological constant.
So like empty space isn't really empty. It has this energy that's pushing everything apart.
It's one possibility. Another is that our understanding of gravity needs an upgrade. Maybe there's a new force or a modified theory of gravity we need to discover.
Wow, that's both exciting and kind of scary. Okay, so we've got these cosmic mysteries, but what about something a bit more specific? Have you heard of the Hubble tension?
Oh yeah, the Hubble tension. It's this weird thing where different ways of measuring the expansion rate of the universe give us slightly different results.
So, like, our cosmic measuring sticks don't agree.
Exactly. And it's a big enough difference that it can't just be measurement errors. It's a real head-scratcher.
So what does it mean? Are we missing something fundamental about how the universe works?
That's the million-dollar question. It could mean our models of the universe are incomplete, that there's some new physics we need to figure out.
Or maybe we just need to find a better way to measure cosmic distances.
Could be. But it's also possible the Hubble Tension points to something much bigger, a major shift in our understanding of the universe.
That's both exciting and a little bit terrifying. Okay, I think we need to take a break from all this mind-bending stuff for a bit.
Agreed. We can always pick it up later. It really is remarkable how much we've learned in, just a few decades. But the universe is this vast, mysterious place, and every answer seems to bring even more questions.
It's true. It's like peeling back layers of an onion. Every time you think you've got it figured out, there's another layer underneath, even more mysterious.
Great analogy. And speaking of peeling back layers, let's talk more about those neutron stars, specifically those pulsars we mentioned earlier.
Okay, remind me, what makes pulsars so special again?
Well, neutron stars are already mind-bogglingly dense, right? But imagine that incredibly dense object spinning rapidly like a beacon and beaming out radiation as it rotates. That's a pulsar.
So these things are basically neutron stars on a cosmic spin cycle, flashing their beams across the galaxy, like they're sending us signals.
That's a great way to put it. And they spin at incredible speeds. Some rotate hundreds of times per second. There's one PIR J7748-2446 ad that spins 716 times per second.
716 times per second. That's like faster than a blender. If it spun any faster, wouldn't it just rip itself apart?
It would. Centrifugal force would tear it to pieces.
Intense. But what makes them spin so fast in the first place?
It's all about how they form during a supernova. When the core of a massive star collapses to form a neutron star, its rotation increases dramatically. Think of a figure skater pulling their arms in. As they spin faster.
So the smaller it gets, the faster it spins. Makes sense. But pulsars aren't the only weird thing about neutron stars, right? We talked about magnetars, those ones with super strong magnetic fields.
Oh yeah, magnetars are like pulsars on steroids. They've got these crazy strong magnetic fields, trillions of times stronger than Earth's magnetic field. And that can lead to some wild effects.
Like those starquakes you mentioned.
Exactly. Imagine a sudden shift in the core of a neutron star, like a tectonic plate shifting on Earth, but on a much larger scale.
So like a neutron star earthquake.
Basically. And these starquakes can release huge bursts of energy, including gamma rays and X-rays that we can detect here on Earth. In fact, one of the most powerful energy bursts ever recorded came from a magnetar about 16,000 light years away.
That's a lot of power. So we've got these spinning pulsars sending out beams of radiation, and we've got magnetars with their insane magnetic fields and bursts of energy. Neutron stars are definitely keeping things interesting.
They are, and the crazy thing is we're still discovering new and surprising things about them. Like in recent years, we've started picking up these strange signals from neutron stars that we don't quite understand.
Oh, like what kind of signals?
Well, there are these things called glitches, where a pulsar suddenly speeds up its rotation for a short time. It's like it gets a sudden boost of energy, and we're still not sure what causes it.
A glitch. That's bizarre. You'd think something as dense and stable as a neutron star would just like randomly change speed.
You would think so, but the universe likes to keep us on our toes. One theory is that these glitches might be caused by the superfluid interior of the neutron star.
Superfluid. Hold on, remind me what that is again.
A superfluid is this bizarre state of matter where it can flow without any friction at all.
So you're saying there might be a kind of frictionless liquid inside these incredibly dense objects? That's wild.
It is pretty wild. We're still trying to figure out how it all works.
Okay, random question. Could there ever be life near a neutron star? It seems like a pretty rough neighborhood.
Now, that's a really interesting thought. It's certainly a challenging environment with all that gravity and radiation, but some scientists have speculated that it might be possible under the right conditions.
Really? What kind of conditions would that even take?
Well, imagine a planet orbiting a neutron star, but not too close. If it had a really thick atmosphere to block the radiation and a strong magnetic field to deflect those charged particles, it's possible liquid water could exist on the surface.
So, life in the shadow of a neutron star, what would the sun look like from a planet like that?
It wouldn't be like our sun at all. It would be this tiny, incredibly bright pinprick of light. And since pulsars spin so fast, that point of light would actually appear to pulse like a cosmic lighthouse beacon.
Wow, that would be amazing to see. It really makes you wonder what other weird and wonderful forms of life might be out there, adapted to environments that we can barely imagine.
Exactly. It shows us that our definition of habitable is probably way too limited. Life is incredibly resourceful.
It really is. Okay, so we've covered planets, black holes, neutron stars, but we can't forget about the stuff that makes up most of the universe. You know, the elephant in the room, dark matter and dark energy.
Ah, yes, the great cosmic mysteries. It really puts things in perspective, doesn't it? We've been studying the universe for centuries, but it turns out most of it is made up of stuff we can't even see.
Yeah, it's kind of humbling, isn't it? So what we actually know about dark matter and dark energy, How do we even know they exist if we can't see them?
It all comes down to gravity. We see the effects of their gravity on the stuff we can see. Like dark matter provides the extra gravity that holds galaxies together. Without it, galaxies would just fly apart.
So it's like the cosmic glue holding the universe together.
Pretty much. And then you have dark energy, which is even stranger. It's what's causing the expansion of the universe to accelerate.
Wait, so the universe isn't just expanding, it's expanding faster and faster?
Yep, that's what the observations tell us, and we have absolutely no idea what dark energy is or how it works.
It's like the universe is playing a cosmic joke on us, saying, think you've got me figured out, think again. But seriously, are there any theories out there about what these things could be?
There are tons of theories, but no definitive answers yet. Some of the leading candidates for dark matter are these hypothetical particles called WIMPs and axions. And for dark energy, well, it could be a property of space-time itself, like Einstein's cosmological constant that he later dismissed.
So you're saying empty space might not be so empty after all, that it has this inherent energy that's pushing everything apart.
That's one possibility. Another is that our current understanding of gravity is incomplete, that there's a new force or a modified theory of gravity out there that we need to discover.
Wow, it's mind-blowing to think about all the things we still don't know. But hey, that's what makes exploring the universe so exciting. Speaking of things we don't know, have you heard of this thing called the Hubble Tension?
Ah, yes, the Hubble tension. It's this puzzling discrepancy between different ways of measuring the expansion rate of the universe.
So, like our cosmic measuring sticks aren't agreeing with each other.
Exactly, and the difference is significant enough that it can't be explained away by just measurement errors. It's a real mystery.
So what does it mean? Does it mean we're missing something fundamental about how the universe works?
That's the big question. It could mean that our current models of the universe are incomplete, that there's some new physics out there that we haven't discovered yet.
Or maybe we just need to figure out how to measure cosmic distances more accurately?
That's certainly a possibility, but it's also possible that the Hubble tension is pointing to something much deeper, a paradigm shift in our understanding of the universe.
That's both exciting and kind of scary at the same time. Okay, I think we need to take a break from all this heavy cosmic stuff for a minute and come back down to Earth for a bit.
Sounds like a good plan. We can always pick up where we left off later.
Okay, I think my brain is finally caught up. Black holes, neutron stars, gravitational waves, it's a lot to process.
It is a lot to take in, but that's what I love about the universe, you know? There's always something new and amazing to discover, something that challenges our understanding of how everything works.
So true. And it's not just those big, dramatic events like black holes and supernovae. Even something like a planet can be incredibly strange when you really think about it.
Absolutely. Remember we started talking about exoplanets? It's a good place to come back to, I think. The sheer variety of planets out there is mind-blowing. It really shows us that our solar system is just a tiny sample of what the universe has to offer.
Totally. Remember those hot Jupiters we talked about, the ones that are so close to their stars, their atmospheres are practically boiling away. And then you've got those super-Earths and mini-Neptunes.
Right, and some of those might have huge oceans, maybe even be completely covered in water. And who could forget about those rogue planets just drifting through space all alone?
Lone wanderers. It makes you wonder if there could be life on those rogue planets. You know, life that doesn't even need a star.
It's a fascinating thought. It really challenges our whole idea of what habitable even means.
It does. It makes you wonder what else is out there, just waiting to be discovered. What other kinds of planets, what other kinds of stars, what other, well, everything.
That's what's so great about astronomy. It's a field that's constantly evolving with new discoveries all the time. And with those new telescopes coming online, like the James Webb Space Telescope, we're going to see even more groundbreaking discoveries in the coming years.
Speaking to the James Webb Telescope, I'm so curious to see what it finds out about those potentially habitable planets in the TRAPPIST-1 system.
Right. 3 Earth-sized planets in the habitable zone. It's begging to be studied further. The James Webb Telescope is going to be able to study their atmospheres in incredible detail, which should give us a much better idea of whether they could actually support life.
And who knows, maybe it'll even find direct evidence of life.
That would be amazing, a truly historic moment. But even if we don't find life on those planets, the James Webb is going to revolutionize our understanding of the universe in so many ways.
It's exciting to think about. But for me, what really blows my mind is when we connect these amazing discoveries to the bigger picture, you know, to our place in the universe.
I totally agree. It's one thing to learn about black holes and neutron stars and the abstract, but it's something else entirely to realize that the atoms in our bodies were literally created in those stars billions of years ago.
Right. That sense of connection, that realization that we're all stardust. It's incredible. It makes you wonder, What's next for us as a species? Will we ever travel to those distant stars and planets? Will we figure out what dark matter and dark energy are? Will we finally unlock all the secrets of the universe?
Those are some big questions, and honestly, I don't have the answers. But I do believe that our curiosity, our drive to explore and understand, is going to keep pushing us forward. We'll keep searching for new knowledge and keep expanding our understanding of the universe.
It's like we're on this epic journey, and we're just starting to figure out where we're going.
And that's what makes it so exciting. The universe is full of wonder and mystery, and there's always more to learn.
I love that. Well, this has been an incredible deep dive. Thank you so much for joining me.
My pleasure. And to everyone listening, keep looking up at the stars and keep asking those big questions. The universe is full of surprises.